Hey, welcome back to my Introduction to Mathematical Proofs playlist. We'll be tackling an interesting problem proving closed forms. Before we talk about that, let's just be happy that we're done with all the logic, right? The next three videos slash episodes are going to be a little connected, and after that, we can return to the line of functions and we can start our bridge into the second half. So we're about halfway through the first half, so we're technically a quarter through. The way that I introduce this topic is going to be very limited, but I believe the motivation is incredibly valuable. Let's say I task you with this task, adding every natural number from 1 to 100. How would you do that? And the naive among us, me included, would start adding them up on a calculator and writing down the results. And while it takes some time, it's somewhat easy. And some others might even write up some code to do so. And indeed, writing up code does seem more favorable. But what if I ban calculators? No calculators, no computers, no nothing. And you have to sum up to 1000 instead. Then you're like, oh man, this is not gonna work. But maybe some of you notice this very interesting thing. We can match up numbers. So let's look at the case of summing up to 100. We can match up the number 101 and match up 99 and 2 and match up 98 and 3. And we can create pairs, and every single one of these pairs add up to 101. And there are exactly 50 of them, or half of how many we have. And then you just multiply them together. 101 times 50 is 5050. And that's actually the number we expect. And surprisingly, this works for odd numbers as well. So let's say we were to sum up to 99 instead. Well, each pair, 1 and 99, 2 and 98, 3 and 97, you match a beginning with an end, so they add with the same number, they add up to 100. And we get 49 pairs, but the middle one, the number in the middle is 50, so it kind of acts like half of a pair. So we get 100 times 49 and a half, and this is 4,950. So we say that when we sum up 1, 2, 3, all the way up to some, let's say, random natural number k, this is the same as k multiplied by k plus 1, all divided by 2. Notice how up above we have, in the even case, summing up to 100, we have 101 times 50. 50 is 100 divided by 2. There's actually another really cool way to think about this as well. Let's say that we have a grid and we just draw a triangle of arbitrary height. So let's say here we chose height 4. Then we're going to color every single one of the squares that the triangle covers. And you're like, okay, well, look, the first row is 1, second row is 2, third row is 3. That's how many grid squares they contain. So 1 plus 2 plus 3 plus 4, this is 10. Okay, so how would we get this number? How would we find out how many grid squares are covered by this triangle? And you might think, it's a triangle, base times height. Well, the base is 4, height's 4. That's 16. Divide by 2, that's 8. That's not 10. Maybe, it seems like we're missing a very interesting thing in the top right corner. So if you were to draw the exact same triangle, but flipped, and cover in how many grid squares that triangle covers, it also does 10. But now when you look at the picture, you get a rectangle. And you're like, okay, what are the dimensions of this rectangle? Well, it's the height, how much we have. So in this case, it's 4. And then it's the base, which is the same as the height, plus 1, because we're shifting it over by 1. But because we only want half of it, or what our triangle covers, we need to divide that by 2. So that's how we get k multiplied by k plus 1 divided by 2. K is the height, k plus 1 is the base, or that added 1. So that's the area of the rectangle, and then we divide by 2 to get half of the area of the rectangle. And that's also another interesting way to think about this. But how can we prove this? Is there any way to prove this from a purely algebraic perspective? And, maybe finding these is going to be a little difficult, but proving, yes, we can actually prove this identity purely algebraically. We don't need intuition. And we can abstractify this method into something that's really interesting and really general. Before that, we're going to have to introduce some notation called sigma notation. So we can write 1 plus 2 plus all the way to k as, well, this weird thing. So it's a sigma, it's a capital sigma. Underneath we have I is equal to 1, above we have k, and to the right we have I. What does this really mean? The number underneath tells us where to start. So the I acts like our index, and we're saying, okay, let's start by letting I equal to 1. Then the number above tells us where we stop to. So we're going to stop at the number k. We're like, okay, wait, but what do you mean stop at? Well, we're implicitly implying that every time we repeat the addition, we're going to increase I by 1. So the first time we add, we're just going to set I equal to 1. Then the next time I is going to be equal to 2. And then we add that number. And the next time I is equal to 3. And we add that number up until I is equal to k. But then what are we adding? That's the thing to the right. That's the expression to the right. In this case, it's just I itself. So when we expand this out, it becomes 1. Since I is equal to 1, then what do we add? Well, I goes up by 1, so it becomes 2. So we add 2. Then what's the next thing? Well, I then becomes 3 since we add 1. So then we add 3. then I becomes 4, so then we add 4 all the way until we stop at I is equal to k. So we stop at adding k. And this is sigma notation. So it's compact, right? That's the reason why this is nice. And I really do like writing out the dot dot dot. It makes me feel like, wow, this goes on forever. But it gets kind of long to write and gets a little annoying. And there's some cool properties that sigma notation has. But for that, let's actually evaluate and think about what these two examples right here would be. So the first thing, we're going to start at I is equal to 3 and end at I is equal to 6. And we're going to add up the terms 2I squared. So the first thing that we're going to add is 2 times I squared. Well, the first time, I is equal to 3, so we get 2 times 3 squared. And then we increase I by 1, so we get I is equal to 4. And then we add that. So we plus 2, and then what's I? In this case, it's 4. I is equal to 4. So you get 2 times 4 squared plus 2 times 5 squared plus 2 times 6 squared. And let's look at the second one. Well, I is equal to 2, so we start at 2. And then we're going to add up to 10. So we're going to I squared plus I. So when I is equal to 2, it's 2 squared plus 2. The next time we add is going to be 3 squared plus 3. Next time we add is going to be 4 squared plus 4. And maybe if you see it algebraically, instead of me just saying it out loud, you'll see exactly why this is the case. So on the first line, we have 2 times 3 squared plus 2 times 4 squared plus 2 times 5 squared plus 2 times 6 squared. See how I increments by 1 every single time? And what's really interesting here is that we can factor out the 2 all the way outside. So this hints at the nice property of sigma notation where we can factor out a constant all the way in the front. Let's look at the next example, I squared plus I. Well, this is 2 squared plus 2. Well, that's our first term. And the next term is going to be 3 squared plus 3 because it goes from 2 to 3. And it's going to be 4 squared plus 4 plus 5 squared plus 5. All the way at the end, it's going to end at 10 squared plus 10. And you can actually rearrange this. This is all addition. The brackets are only there for us to keep track of what each term is. So the first term, where we only have the 2, I is equal to 2, we can just rearrange it to get 2 squared plus 3 squared all the way to plus 10 squared, plus 2 plus 3 all the way to plus 10. And then we can just collapse that back into sigma notation. Why would you want to do this? It's just nice and easy to work with. And it's just there to demonstrate a point. Of course, you can evaluate this, but that's not really our purpose here. That's not really what we're trying to do. And these are some of the rules that we can derive or think about. These are some interesting properties. For any value of c that you have, if you have c times, let's say, I, where we start at j and end at k, in our sigma expression, we can just factor out the constant in the front. In our first example, we can factor out the 2. And then we can split expressions. So for any expressions a and b, let's say a is I and b is I squared, we can split them. So we can actually just split them. It's kind of like what we did in example 2. And then the third thing we can do, or a third property, is we can split sums. So let's say that we want to go and sum I, starting from number j, let's say 3, I don't know, it doesn't really matter what the number is, all the way up to k, let's say that's 10, we can actually split it up with a number in between. So if you've done integrals, a lot of these should be very, very similar because it's actually the exact same thing. So what we can do is split up where the endpoint is. So if we start at 3 and sum to 10, it's the same as starting at 3 and summing up to 6, and then adding the sum from 7 to 10. It's the exact same thing. All that's happening is we're changing the endpoints, or we're putting something in between. And for the last one, any time that we have a constant and we're summing up the constant, how many times you sum the constant is dependent on how many times you go through the sum. So if I is equal to j and we go all the way to k, then the amount of times that the loop repeats is k minus j plus 1. Think about why that makes sense. And because we're adding the same number every single time, well, then we just multiply it. For example, if we have I is equal to 1 all the way to 10, and all we keep doing is adding 5, we add 5 10 times. That's the same as 5 times 10. So what's really interesting is that you can prove these properties. I understand that explaining them via words is a little difficult, but if you were to actually prove them and understand how to algebraically form them, you're like, okay, I understand how this works. So do them. They're surprisingly easy to do, and all you really need to do is expand out the expression and rearrange the terms. So if you don't understand what the rule is saying or why it's true, go ahead and prove them. Now back to closed forms. So a closed form is an expression or a formula that doesn't rely on previous terms. So before we did 1 plus 2 plus 3 plus 4 plus 5 and so on. If we solve 1 plus 2 plus 3 plus 4 plus 5, we get 15. But then what if we add 6? Previous stuff actually matters, so we can do 15 plus 6. So what we're doing is we're using the previous cases or previous iterations to solve the new ones. So this is, you can think of it as repeating something or recursion if you're familiar with coding. What you're doing is you're using previous cases. What we want to do is find a closed form or something that doesn't rely on the previous cases. As in, it doesn't matter what 1 plus all the way to 5 is. If you just have the number 6 and you want to find what it is to sum it up to 6, we can just solve it by plugging it into a formula. This is a closed form. The technique that we're going to learn and use to prove these closed forms or prove these formulas is a little uninspired. We lose part of the intuition while proving these closed forms. I mean, we showed how 1 plus 2 all the way to k is the same as k multiplied by k plus 1 all divided by 2, and we're going to have to prove that. That's a closed form or a formula since it only depends on k. It doesn't depend on everything before it. And in our attempt to prove that, the tool that we're going to use loses the intuition or the cool factor of that, oh, here's the grid, here's the triangle, and adding all of these up together. And that's kind of the price that you have to pay when you're going from something that's beautiful to something that's purely algebraic. Once again, we're developing tools, and I'm just giving you one example of why we would want this tool. And we're going to actually talk about this tool in the next video. So the idea is this. Our motivation for discovering this new tool is proving closed forms or formulas for summations, adding something over and over and over again, or like 1 plus 2 plus 3 plus 4, all the way up to a certain number. Or let's say I told you to prove 1 squared plus 2 squared plus 3 squared all the way up to k squared. How would you prove that? How would you prove it, right? That's what we're going to discover. That's a tool we want to learn. Okay, I'm really excited for the next video. This is one of my favorite things in the course, so I will see you next time.